Section 11 in the Klein's Organic Chemistry textbook, second edition, chapter 21, talks about reactions of esters. Now, this is a pretty big functional group. It's fairly common, and there are quite a number of different reactions we can do with esters. The first reaction that you can do with an ester is a saponification. Okay. Saponification is one way that, triglycerides are changed into soap. So let me show you the reaction that I'm talking about here. So if you have a long chain, carboxylic acid derivative with, like, say, an ethyl group there, you can do a reaction between this and sodium hydroxide. And then, a mild acid, kind of like acid workup. And what this will give you is a carboxylic acid and the alcohol. So it's kind of a reverse reaction of the Fischer esterification. Okay? The reaction mechanism here is quite easy. It's a little bit short. Okay? So in the first step, hydroxide, which is your nucleophile, is once again, as usual, going to attack the acyl carbon. Electrons move up towards the oxygen. And since this reaction is done under basic conditions, it's okay to have these negatively charged oxygens throughout the mechanism. You'll see what I mean here. So we have A for attack here. And at this stage, we kind of break one of the rules that we've talked about very early on in the class. We said OH minus is not a good leaving group. But here what we're doing is we're kicking off RO minus, which generally speaking is not a good leaving group, but it is possible to leave in this case because you have an internal nucleophile. Okay? So it's kind of an exception. This is the elimination step. And what you get here is strangely enough, carboxylic acid, and you have, an alkoxide. Now, probably it's water that mediates the deprotonation and protonation, but I'm just going to go ahead and use the alkoxide here to remove the amoracidic proton and give you the product there. Okay, so the alcohol is being protonated and the carboxylic acid is being deprotonated. So it's AED or AEP, however you want to write this. Okay, so 3 steps. And H3O plus is there just to make sure that you protonate. Well, let me take it slow. Okay, so in this step, what you have occurring is you have your carboxylate, right? Because under basic conditions, you're going to have a carboxylate and you're going to have your alcohol, okay? And the second step, you're adding H3O plus. So let's just go ahead and draw that step here. We have H3O plus and the negatively charged oxygen here, okay, is going to grab a proton from your acid, and that's going to give you the final products there, okay? So we'll label it like that for this. Okay, so that's the saponification of esters, and that's how soap is made. There's a little figure in your book. I'll let you look at that rather than me talk about that. There's another way to hydrolyze esters, and that's the acid-catalyzed hydrolysis. Okay, so acid catalyzed hydrolysis of esters. Okay, so if we have a carboxylic acid that looks like this, an ester that looks like this, and we treat this with water and acid, which we normally just write H3O plus to simplify the reagents, you will make a neutral carboxylic acid, which is the acid form, and a neutral alcohol. Okay? And this mechanism follows the usual PAD-PED. You have protonation, attack, deprotonation, protonation, elimination, and deprotonation. And this is the mechanism 21.8 in the Klein's book. Okay, so I'll show you the mechanism now. In the first step, you want to, okay, so if you have acid in your reaction mechanism, you want to use that in the first step. And I mean acid in the reaction arrow, you know, H+, sulfuric acid, H3O+. And here, when we're dealing with esters and carboxylic acid derivatives, as usual, you want to protonate the carbonyl oxygen first, okay? I know there's another oxygen, but this will lead us down the correct path, okay? Now that we have a strong electrophile, we can attack this with just neutral water. As usual, you want to attack the carbonyl carbon, okay? And electrons go up towards the oxygen. All right? And that's going to give you an intermediate, which we call the tetrahedral intermediate. And things, as usual, can get kind of confusing because you have all of these oxygens all bonded to the same carbon. But once again, remember that we are trying to do a nucleophilic acyl substitution. That is to say, we want to kick off this group right here, okay? Now, since we are operating under acid conditions, we don't want to kick off O-, okay? So this mechanism has no oxygens with a -1 formal charge, okay? That's really important to recognize. We have acidic conditions. That means there's no alkoxides or hydroxide floating around. So what we need to do instead of immediately kicking off the OCH3- is to take water, which is present, and do a number of different proton transfers. Okay, so first we're going to deprotonate this guy here. Okay, and then what we want to do is protonate this oxygen. Okay, so everything's formal charge of 0 or -1. Okay, so we want to protonate here, and then what we get is an intermediate. And I'll just use a different colored pen here just to highlight what we are doing. So this is the good leaving group right here, and the neutral methanol can be kicked off this molecule. Okay, so this reforms a carbonyl, and we break this carbon-oxygen bond. And this is the key step here. Okay, we're doing an elimination reaction at this stage. We're kicking off methanol. Okay, so that's the product here that's being formed, and all the other bits and pieces form a protonated carboxylic acid. Okay, and now we want to deprotonate that. What do we have in solution? We have mostly water. We do have methanol, which could do this reaction as well, but I would prefer you to draw water. Okay, and we deprotonate that, and we get propanoic acid, okay, as the product, and methanol. Okay, so let's look at the steps here together. We've got in step 1 we have protonation. Okay, step 2 we have attack. Step 3 we have a deprotonation. Step 4 we have a protonation. Step 5 we have an elimination, and step 6 we have a deprotonation, or PAD-PED for short. Okay, so that's the acid-catalyzed hydrolysis. Okay, hydrolysis means hydro is water, water is breaking, and lysis means break. Okay, so hydrolysis means water is breaking up the ester into a carboxylic acid and an alcohol. All right. The third reaction you can do with esters is to do something called aminolysis. Okay, I'll write in the title here of the reaction. Okay, so lysis means to break, and amines, like primary amines or ammonia, for example, can do that. So if I have an ester like this, for example, and I treat this with ammonia, okay, it's possible to form the amide and an alcohol. The textbook gives you a warning. It says it's not very practical because this reaction is very slow. Okay, and which means you have to wait a very long time. All right, and so let's go ahead and just show the mechanism here for completeness. If we have ammonia, which is not a very good nucleophile, okay? Why is it not very nucleophile? Well, it's a semi-good nucleophile, but the ester is resonance stabilized. So we don't really have a strong nucleophile. We don't have a strong electrophile. We have a mediocre electrophile and a mediocre nucleophile. So this is definitely the slowest step in the reaction, okay? And you're going to form your tetrahedral intermediate, okay? You're going to kick off butoxide, butoxide then is a strong base. Ammoniums are strong, weak acids, and so you'll form that product. So we have attack, we have elimination, and then we have protonation and deprotonation of the different parts, okay? So AD, AP, however you look at that. So not very practical, but I'm putting it in here in this video just for completeness, okay? Now let's talk about some very important reactions. What number are we on? We're on number 4, okay? Let's talk about the complete reduction of esters. Now, we've learned this before in section 20, well, I guess we've learned it before. I don't remember the mechanism going over it, but we learned about it when we talked about alcohols. So if we treat this with lithium aluminum hydride is always excess, so I never write excess above the arrow here. And then if you treat this with water, what you form are 2 alcohols. Okay? Let me go ahead and show you what the mechanism is. So in my class, I just always write H- for my hydride, okay? That, of course, is going to attack. It's a very strong nucleophile. It's negatively charged here, and that's going to attack the esters quite readily. And this is going to give us the, tetrahedral intermediate. I guess I'll draw the H going down on the bottom there. And we have OMe here, okay? So here we want to remember hydrides are basic. And so we remember that from the alcohol chapter. So it's okay to have negatively charged oxygens here. It's okay to kick off methoxide. So we eliminate and make an aldehyde, okay, and methoxide, okay. The next step is that since we have excess lithium aluminum hydride here in the reaction, hydride is going to attack a second time, and we learned about the reaction of aldehydes with hydride, and those give us alcohols. Okay, so we've got this alkoxide here, which is butoxide, and this other one, which is methoxide. Okay, so that just sits there for a while until we come along, and then in step 2, we add water, okay? So this guy gets protonated, okay, to give us this butanol. And this guy gets protonated with large excess of water that we're adding in to form methanol. Okay, so it's AEP, you know, P and P, protonate and then protonate. Okay, so this step is a protonation step. So the three-step sequence is attack, eliminate, and then protonation. All right, so that's what I call the complete reduction of esters. You form all the way down to the alcohols. Okay, and just remember that lithium aluminum hydride is always excess. Okay, now we do have a way to stop at the aldehyde. So I call this the partial reduction. Okay, and we want to use what's called dibal. Now, Klein's textbook calls it dibal, and the Smith's organic chemistry textbook calls it dibal-H, and I like dibal-H. Dibal stands for diisobutyl aluminum hydride, and it has this structure here. Okay, and the mechanism is a little bit more complicated than what I'm showing here, but I'm going to treat this as hydride, and the only thing you need to remember is that since it has one hydrogen in the reagent, it's only going to add hydride once. So that previous molecule, let's do the reaction. We had methyl butanate. Oops. And if I treat this with a dibal, okay, and once again we add, you know, water here. Okay, what's going to happen is we're going to form an aldehyde in principle and an alcohol. Okay, so how does this mechanism work? Once again, if you have these funny hydride, lithium aluminum hydride, or lithium triisobutoxy aluminum hydride, or this weird thing, dibal-H, just use hydride to attack. Okay, swoop the electrons on up to the top. Okay, and I'll put this in quotes so you really know that this is not fully correct, but Klein's book doesn't even have this in here. Okay, so what we want to draw now is the tetrahedral intermediate, as we normally would. Okay, and we've added this hydrogen. And now, since we're under basic conditions, we want to kick off or eliminate. So this first step is attack. Second step is eliminate. We want to eliminate methoxide, okay? And the reaction stops there at the aldehyde. Okay, so dibal will not react with the aldehyde. So it stops there, it stays there, and we have methoxide floating around. Okay. Now the purpose of adding water is to protonate the alkoxide, but usually you're throwing away the alcohol, especially if it's a, you know, something methyl or something. All right, so that's going to be a protonation step. So A for attack, E for elimination, and then P, protonation at the end. Okay, so it's a three-step reaction. So just remember, dibal-H is a controlled reduction. You're only adding one hydride, and it's still a nucleophilic acyl substitution. You're substituting this methoxy group for a hydrogen. Okay. The sixth thing that esters can do are react with Grignards, and we saw this again with the alcohol chapter, so it's a little bit of review. So Grignards and esters. So let's take a look at, we'll use this same ester again. Well, we grew it by one carbon, but that's fine. So we'll do a methoxy, okay, a methyl pentanoate. And we'll treat this with two equivalents. Now, we normally write just excess. Let's do excess ethyl magnesium chloride to be specific. And then we'll add water there, okay? And what we get here is a tertiary alcohol where we've now incorporated two ethyl groups into the molecule. And we spit out methanol there, okay? HOME, all right? So how does this reaction work? It works just like we saw with acid chlorides, and the textbook actually does show a mechanism there, 21.10. So what you've got is a nice carbanion nucleophile, okay? So if you're doing this curved arrow reaction mechanism, you just want to show a negative charge on your carbon, attacking the carbonyl carbon. You don't need to worry about the magnesium and the chlorine and all that other stuff of the inorganic parts. So you want to attack your guy there, and you get the tetrahedral intermediate. Okay, and I'll just draw a line drawing for the ethyl. Now remember that Grignards are extremely basic. Since this is a basic reaction mechanism, we can just kick off the methoxide, which is also a base. And so that's an elimination step. And look at that, we form a ketone. The ketone can react with an additional equivalent of ethyl magnesium chloride. And it does so just like how we saw in the aldehyde and ketone chapter. We attack the carbonyl carbon and we form an alkoxide. Now there's no good leaving group here, so it just hangs out for a while. But now you have those two ethyl groups there, okay? And like I said before, that kind of just sits around until you add water. When you add water to the reaction mixture, you're going to protonate that alkoxide to give you methanol, and you're going to protonate this alkoxide, okay, to give you that alcohol. Okay, 3-ethyl, 3-heptanol. All right, so that's protonation at that step. So it's AEAP, okay? 2 P's if you really want to count the exact different parts. But if we're doing synthesis, usually we're interested in just the larger organic molecule, and we're just discarding methanol. It's just a tool to allow us to do this transformation, okay? So that's a very nice reaction of esters that you can do. Let's do a practice problem now in the textbook, and I think that will conclude this section. All right, so problem 24, they just want us to draw the products. Now sometimes you have a small little bit, but we're going to focus on the carbonyl part of the molecule, okay? So here we're going to do excess lithium aluminum hydride, and so there's my carbonyl carbon. What I need to draw here is the alcohol at that carbon. So there's my carbon, and I just want to draw an OH, okay? So that definitely is the main focus. I'm not sure how critical your professor is, so we need to draw methanol as well, right? Where does that methyl group go? That forms methanol, okay? This next one here, we have this ester, in B we have this ester, and then we're adding excess ethyl magnesium bromide and water, okay? So again, we're going to discard the methanol there. That's always going to be a product. And so you're going to form an alcohol where that dotted carbon is connected to the hydroxyl group and your 2 ethyl groups. Okay, so the 2 ethyl groups have been connected to that carbonyl carbon, and yes, you form methanol. Okay. In molecule C, it's very important to think about this reaction. So remember again that this bond right here is broken. The ester bond, we'll call it, is broken. this carbon becomes an alcohol, and this carbon becomes an alcohol. So what you're going to form from this is a diol with a total of 5 carbons. Okay, so you're going to have a hydroxyl group attached to, carbon 1, and carbon 5 is going to be an alcohol as well. So you might just make a note of that if you're a little bit confused about. This functional group is called a lactone. We've talked about it before. Lactones form diols, okay, diols at the very beginning and the very end of the chain. So they sometimes call it an alpha omega diol, okay? Alpha means first, omega means last, basically, okay? In molecule D, we have an ester, an H3O+. So remember again, you form a carboxylic acid and an alcohol. So it might be easy to see for most of us what the carboxylic acid is going to be. It's going to be with that 6-membered ring there. And the alcohol is going to be ethanol. Okay? For molecule E, we have sodium hydroxide, remember? So what that does is it removes this hydrogen. You get an alkoxide, and then it attacks ethyl iodide, and it kicks off the iodide. So we're going to get the ethyl ester from that. The name of that is ethyl benzoate. Ethyl benzoate. Okay? In molecule F, we have a lactone. So watch out for those lactones. Okay? Lactones, when that ester bond gets destroyed, is going to make a diol, right? You're going to have a hydroxyl group on one carbon and a hydroxyl group on the other carbon. Now watch out, when you add ethyl magnesium bromide, remember that that's going to install not 1 but 2 ethyl groups on that top carbon. So what you get from this is the aromatic ring stays there, okay, and we'll just put a dot on that carbon to orientate ourselves. So we have a hydroxyl group, we have 2 carbons, okay, and on the other side of the molecule, we have just 2 carbons, which I messed up there, 2 carbons, and then a hydroxyl group attached to that dotted carbon, okay? So that's it for this. I hope these practice problems get you started on additional practice problems in the textbook. Thanks for watching, and please consider subscribing.